Okay, so the phrase differential equation probably sounds a little scary, right? A bit intimidating. But it's not just some abstract math concept. It's actually the fundamental language that describes change. Everything from how a population grows to how heat spreads across a room. Today, we're going to build a visual map of that language.
So let's kick things off with a big question. Imagine you wanted to predict the path of a leaf floating down a river. You wouldn't really need a map of the entire river, would you? You just need to know the direction of the current right where the leaf is. So, what if we could create a map that showed the direction of that current at every single point? Well, that's exactly what we're about to build.
To build this map, we got to get to know our main tool, a specific type of equation that's all about describing change itself.
And here it is, a first-order differential equation. Now this is where it gets interesting, because this isn't like the algebra you're used to. It doesn't give you a single answer like x equals 5. Instead, you feed it a location, a coordinate, an xy point, and it spits back a slope, a rate of change. It's a tool for finding the direction of the current at one precise spot. And this is the key takeaway here. The information is local. Think of it like a huge grid of tiny little signposts. At any single intersection on that grid, the equation acts as the signpost, telling you exactly which way to go next. Each signpost is just one small piece of a much, much bigger puzzle.
So one signpost is helpful, sure, but what happens when we can see all of them at once? Well, that's when those individual directions suddenly combine to build something incredibly powerful.
So each of those little signposts, well, it has a fancy name, a lineal element. It's just a tiny line segment at a specific point, tilted at the exact slope that our equation gives us. This is the fundamental building block of our map. It's one single arrow showing the way.
Okay, so what happens if we just draw thousands of these linear elements all at once? Bam! You get this. This is a direction field. This is our finished map of the currents. Every single arrow shows the direction of change at its point, and you can already start to see the patterns, can't you? A larger flow just seems to emerge from all those individual directions. And that gut feeling you're having, it's spot on. This quote here says it perfectly. The direction field suggests the shape of the solution curves. Think about that. We haven't solved a single thing with algebra yet, but this one picture, this map, already contains every possible path.
Okay, now here it is. This is the big aha moment. On the left, we've got the direction field, our map of tiny arrows, and on the right, those are the actual solution curves. Look at how they just snap together perfectly. The curves are simply following the flow that the arrows dictate. They are the paths you would trace if you were just connecting the dots of the direction field. It's amazing.
Okay, but wait, our map shows like an infinite number of possible paths. So how do we know which one is our path? To do that, we need a starting point.
This idea is called an initial condition. Let's go back to our leaf in the river. If you want to know where it's going to end up, you have to know where it started, right? It's the same thing here. By picking just one single point that our path has to go through, we can isolate one specific curve out of all the possibilities.
Let's make this real. Here's the direction field for the equation dy dx equals sine of y. Now, if we add what's called an initial condition, something like y of 0 equals -3/2, we're just saying our path has to start at the point 0, -1.5. You can see that point right there on the graph. From there, it's easy, right? We just follow the arrows to trace that one unique solution.
Visualizing this stuff is awesome. It gives you such an intuitive feel for what's going on. But at the end of the day, it's still kind of like a sketch. Now we need the blueprint. We need a way to find the precise formula, the compass, that will give us the exact equation for that path. So how do we do that? How do we go from this beautiful visual map to a rock-solid, exact formula? Well, we need an analytical method. There are lots of different types of differential equations, and each has its own method. We're going to start with one of the most common and fundamental types. Meet the separable equation. And honestly, the name gives the whole game away. It's any differential equation where you can, with a bit of algebra, separate it. Get all the y stuff on one side of the equal sign and all the x stuff on the other. It's a special kind of map, which means it has a special kind of compass. Spotting them is really just a pattern recognition game. Look at the left. dy dx equals xy. Yep, easy. We can just divide by y and multiply by dx. The second one looks tricky, but thanks to some basic exponent rules, that e to the 3x plus 4y is just e to the 3x times e to the 4y, so it's also separable. But this one on the right,
dy dx equals y plus sine of x? Try as you might, you just can't algebraically pull them apart into pure multiplication. That one is not separable.
So, once we've spotted a separable equation, what's the plan? Well, it turns out there's a clear four-step process to get from the equation to the exact formula for our solution curve. Let's walk through it.
Here's the playbook. Step 1, double-check that the equation is actually separable. Step 2, do the algebra. Get all your y terms with the dy on one side and all your x terms with the dx on the other. Step 3 is the magic step. Integrate both sides of the equation. This is what turns those rates of change back into a function. And finally, step 4, just solve the result for y, and boom, you've got your precise formula.
And that's the big connection here. We started with a visual map, the direction field, which showed us the shape of all the solutions. Now, with this method of separating variables, we have an analytical tool, our compass, to find the exact equation for any one of those curves. We've officially gone from the map to the compass.
So, we've learned how to see the flow, how to visualize the entire landscape of solutions, and we've learned how to use our first compass to chart a precise course through it. But this is just our first step into a much bigger world. The next time you see something changing around you, ask yourself, what would its direction field look like? What story is its rate of change trying to tell?